with some simple analogies to help you understand the basics, and then we'll advance it into electrical engineering terms with some worked examples, as well as looking at what is power factor, what is a good and bad power factor, what causes bad power factor, and how to fix bad power factor. So what causes poor power factor? In most cases, the power factor is affected by inductive loads. If we have a purely resistive load, such as an electrical resistive heater, then the voltage and the current waveforms would be in sync or very close. They would both pass through their maximum and minimum point and then pass through the zero axis at the same time. The power factor in this case is 1, which is perfect. If we drew a phasor diagram, then the voltage and current would be parallel, so all the energy drawn from the electricity supply goes into doing work, in this case creating heat. But if we took an inductive load, such as an induction motor, then the coil's magnetic field holds back the current and results in a phase shift where the voltage and the current waveforms fall out of sync with each other, so the current passes through the 0 point after the voltage. This is referred to as a lagging power factor. Earlier in the video, I said the foam or the kVAR is useless to create and maintain the magnetic field which rotates the motor. The reactive power is wasted in the sense that we get no work from it. If we drew a phasor diagram for a purely inductive load, then the current would be at an angle below the voltage line, meaning not all the electricity consumed is doing work. If we took a purely capacitive load, then the opposite happens to the inductive load. The voltage and current are out of phase, except this time the voltage is held back. This causes leading power factor. Again, this will mean that not all the electricity being used is being used to do regardless. If we drew a phasor diagram for a purely capacitive load, then the current line would be at an angle above the voltage line as it's leading. Correcting poor power factor. What can we do to correct poor power factor and reactive power charges? In most cases, we come across lagging power factor caused by inductive loads. To correct poor power factor, we can add capacitors or inductors to the circuit, which will realign the current back into phase and bring the power factor closer to 1. If we have a lagging power factor caused by high inductive loads in the circuit, then we add capacitors. If we have a leading power factor caused by high capacitive loads, then we add an inductive load to the circuit. These need to be calculated, and we'll see some example calculations of this at the end of the video. So why should we fix poor power factor? Poor power factor means you need to draw more power from the electricity network to do the same amount of work. Therefore, the cables need to be larger, so the installation is going to cost more money. If the power factor becomes too low, then the electricity supplier might charge you a penalty fee or a reactive power charge. Poor power factor can cause life expectancy of equipment in extreme scenarios. Capacitor calculations for power factor correction. Let's look at a simplified example of calculating the size of a capacitor to improve the power factor of a load. The building has a 3-phase power supply and has a total load of 50 kilowatts of work. It also has a power factor of 0.78, but we want it to be 0.96 to avoid penalty charges. Currently, the building has a total apparent power, or kVA value, of 64.1 kVA, and we find that by just dividing the kilowatts, 50 kilowatts, by the power factor of 0.78. It also has a reactive power of 40.1 kVAR. We find that by taking the square root of the kVA squared and subtracting it from the kilowatt squared. So take the square root of 64.1 squared minus 50 kilowatt squared. Then we calculate what the value should be if we had a power factor of 0.96. So our apparent power should be 52.1 kVA. We find that from 50 kilowatts divided by 0.96 power factor. Then we find our reactive power, which is the square root of the kVA squared minus the kilowatt squared. So the square root of 52.1 kVA squared minus 50 kilowatt squared, which gives us 14.6 kVAR. The capacitor therefore needs to make up the difference between these, so 40.1 kVAR minus 14.6 kVAR, which equals a 25.5 kVAR capacitor.